Hello, this is Mr. Manley. I'm doing a follow-up to my video on roots of unity. This is Roots of Unity Part 2. If you watched the previous video, you saw that we were able to solve x to the fifth equals -1, and we were able to find 5 solutions. So I just want to take it and push it a step further. The concepts are really there already, but I want you to see them in application, the application of the concepts to a slightly more challenging situation. In this case, I'm going to have x cubed is equal to 1 minus I. So there we have something that's looking a little bit different. The earlier examples that we looked at were x to the fifth equals 1 and or -1, and x to the fourth is equal to 1. So now we're obviously making that a little bit more complex, in fact using a complex number. But the process is exactly the same. See if you can see the relationship, or maybe think about, all right, well, what would the first step be? I guess the first step, if we're going to correlate that to what we saw in the previous problems, is to graph this. Remember, that's what we did with the previous problems. So let me get some graph paper here, and I'm just going to graph this down in the lower right-hand side. I think I would give myself this scale, 1 and 1 on the I-axis and the real axis, so that 1, -1 is down here in the fourth quadrant. Now, what I actually want is I don't want the 1, -1. What I actually want, if you recall, was the first root. And the first root was a lot easier back here. If we look at this, the first root for x to the fifth is equal to -1 was -1. So I was able just to look at where is that -1. That's actually not the case here. So this graph of 1 minus I actually isn't going to help me, because I need the first root. So in order to get the first root, I am going to look at 1 minus I, and I'm going to take the cube root. Now that might seem unmanageable, and it is. I don't know what's the question I need to answer here is what multiplied by itself 3 times is equal to 1 minus I. Well, I don't have that on the top of my head the way I did here. What multiplied by itself 5 times is -1. And I had that. I could do that, -1. Well, here, I don't have that off the top of my head. So look, what we're going to just use some concepts that you've already used if you've been looking at the trigonometric form of complex numbers. So that's where I'm going to start, and maybe you could guess that that's what I'm going to do is I'm going to write 1 minus I as rad 2. So it turns out that this is kind of useful that I graphed this down here, because let's look at it. It has a magnitude. If you look down in the right-hand corner here, it has a magnitude of rad 2. And then what's its angle? That you should be able to just see that, right? That the angle is cosine 315 degrees. Or not cosine 315, it's just 315. So the angle is 315, and then I'm going to write that, the trigonometric form of the complex number, as cosine 315 degrees plus I sine 315 degrees. So there's the complex form right there of 1 minus I, and I'm taking the cube root of that, right? I'm doing the cube root of that. Now, of course, we know that roots can be written as powers, right? So I'm going to write that as to the 1/3. All right, and hopefully you're not getting lost with all the clutter here. So I've got rad 2 times cosine 315 plus I sine 315 to the 1/3. That's going to give me my first root. And how is it going to do it? Remember de Moivre's theorem? You might not know that that's what it's called, but it was raising a complex number to a power, raising a complex number in trigonometric form to a power. So does this look familiar for you from a previous section? Rad 2 to the 1/3. That's how I apply the power to a complex number in trigonometric form. And then here's the big question. Now what, do you remember what happened next? This power, we multiplied it by that angle. So if you don't remember that, go back and look for de Moivre's theorem, or look for a place where you have in your notes that you raised a complex number to a power, and you'll see that. So let's do 315 divided by 3. That's 105. So it's cosine 105 degrees plus I sine 105 degrees. Now at this point, maybe you're kind of lost, but now we're at this point here. This is the same as we were at this point here. We have our first root. So I have my first root there, -1, and then I needed the other 4 roots. So here, this is our first root. Okay, now I'm going to clean that up a little bit on a separate page. All right, so here I've cleaned it up, and there is our first root. And I just changed the rad 2 to the 1/3, and that's the 6th root of 2. You should be able to use your properties of radicals and exponents in order to understand how I did that. All right, now you'll recall this, hopefully, in our previous work with roots of unity. I've got the first root, and it is here. It's right there at 105 degrees with a magnitude of radical 2. So the other 2 roots are evenly spaced, right? There's another one there, and there's another one there. And how do we find those? Well, they're evenly spaced, so I just add. If I have 360 degrees and 3 roots evenly spaced about it, they're 120 degrees apart, right? So I'm just going to add 120 degrees. So the second root, the second solution, is cosine plus 120. So what is that? 225? 225 degrees plus I sine 225 degrees. And then add, this is a 6th root here. This one here, that should be 6th root also. So I'll just fix that. Okay, and then another 6th root of 2, and add another 120 degrees. Cosine, is it 345? Yeah? Plus I sine 345. And there are my 3 roots of unity, which is just to say there are my 3 solutions. So if I took any one of these 3, multiplied by itself 3 times, the result is going to be 1 minus I. Okay? So nothing new, just applying it in a slightly more complex and actually to a complex number that has an imaginary part.